So welcome to lesson on 1112 box F. Here we are going to take a look at the quotient rule, which goes along nicely with the product rule that we took a look at in the last lesson here. So it's very, very similar to the product rule. So let's say that we are given some function. Again, we'll use h at x, which instead of being a product of two functions is instead a quotient of two functions, f at x divided by g at x, where again f at x and g at x are both functions of x and are differentiable everywhere on the domain of h of x, etc., etc., etc. So the rule for finding the derivative h primed at x, this is a little bit more complicated than the product rule, but again still similar. Derivative of h at x is going to be f primed at x times g at x minus f at x times g primed at x. So that part is very similar to the product rule, but we also have to divide this whole thing by g at x squared. Okay? So a little trickier, both because of the negative sign here. The negative sign means that the order of these two terms is important, so you have to know which one comes after the negative sign, or else you get all of your signs backwards. And we still end up with a quotient with something down in the denominator that can be kind of ugly. And as I did with my product rule, the notation that I'm going to look at as we go through our examples is that if f at x is this function u over v, where both u and v are functions themselves, our derivative, f primed at x, is given by u primed v minus uv primed, all divided by v squared. Okay. So I'll just draw, again, that line there to indicate that that's a slightly different notation. So let's jump in here to an example. Okay. We want to find the derivative of this function here, f at x equals 3x minus 4 over x squared plus 5. So the numerator is our u function, 3x minus 4. The denominator is our v function, so v is going to be x squared plus 5. So when we do our derivative, f primed at x, we'll just write out what the quotient rule here is. So u primed v minus uv primed, all divided by v squared. So we want the derivatives of these individual terms. So let's see, the derivative of u, well, let's see, u is 3x minus 4, so the derivative of that is just 3. And then we multiply that by our entire v function there, x squared plus 5. And then we're going to subtract, our u is 3x minus 4. And we're going to multiply that by the derivative of our v function. So v is x squared plus 5. The derivative of that is going to be 2x. And then down on the bottom, we're going to have x squared plus 5, our v function, all squared. When we have something like this, we should simplify this expression here. At the very least, we should simplify the numerator, because we can tell by looking at it that they're going to be like terms that are going to cancel. I probably wouldn't bother expanding out the denominator in something like this. So let's, and why wouldn't I do that? Because often what you want to do is you want to set this, you're finding your derivative, you're going to set it equal to 0, and you're going to solve. If you're setting it equal to 0 and solving, you're really only interested in the numerator, because that denominator is just going to, if the denominator is 0, you get an asymptote, and so on and so on. So let's just simplify the numerator here, which gives us 3x squared plus 15 minus 6x plus 8x. Thank you, 6x squared. And yep, all divided by x squared plus 5, all squared. And we can just sort of collect our like terms there, and we get minus 3x squared plus 8x plus 15, and the denominator stays the same here, x squared plus 5 all squared. And we'd probably just leave it like that. Okay, second example here. Let's find the slope of the tangent to the curve y equals x cubed divided by x squared plus 9 at the point where x equals 1. So once again, we've got a quotient here, so we've got to use our quotient rule. We'll just have u on the top and v on the bottom. And we know that we're going to use our quotient rule here, so let's just write this. We want y primed is going to be equal to, and up in the numerator, remember we want u primed times v, and then we want u and v primed. So let's see, our u function is x cubed, so the derivative is going to be 3x squared, and let's multiply that by v. So we multiply that by x squared plus 9, and then we subtract u is x cubed, and v primed is going to be just, let's see, x squared plus 9, just 2x. And then down on the bottom we want v squared, so that's going to be x squared plus 9 all squared. And I should add in that this is v squared. Okay. So what should we do next here? Next, we could expand and simplify, or we could plug in 1. Is it better to expand and simplify, or is it going to simplify a lot more if we plug in our x equals 1 here? Yeah, let's plug it in. So just a notation thing. When we were subbing it in, when we were using the f at x notation, we did f at 1 inside the brackets. In this notation, to indicate that I'm subbing in a value, I'm going to say y primed. I'm going to do a vertical line here, which means evaluated at, and then I'm going to put x equals -1 down at the bottom of that line. So this is read as y primed evaluated at x equals 1. And this just lets who's ever reading it, namely me, know that at this step you have subbed in a value and then started evaluating. Okay. So let's, yeah, and this cleans up nicely here. I'm going to end up with 3, and then 1 plus 9 minus 1 times 2, all divided by 1 plus 9 squared, which is going to be 30 minus 2 over 100, or 28 over 100, or if we put this fraction in lowest terms, it's going to be 7 over 25. So there's our slope of our tangent. Okay. So it's not always easier if you, it's usually easier if you sub in that x value towards the beginning, because it's easier to simplify using the numbers rather than simplifying using the variables. So let's do one last sort of application type question here. Find the coordinates of each point on the graph of f at x equals 2x plus 8 divided by root x, where the tangent is horizontal. Okay. So before we start working on this, let's just sort of think about what we're going to have to do in order to solve this. So if we're interested in the tangent, what are we going to have to do to our function first off, if we're looking for something to do with the tangent? Tangent tells us, Austin? Yeah, so we clearly need to find the derivative. Okay? If we're interested in the tangent being horizontal, what is that telling us about our tangent if it's horizontal? Or the value of the derivative, I guess. It's going to be 0. So we're going to set f primed at x equal to 0, and then we're going to solve for x. And then once we have x, because we want the coordinates of the point, we can take x, sub it into f at x to get y, because we want the coordinates. So let's start by trying to find our derivative here. And before we do the derivative, I'm just going to rewrite this as 2x plus 8 divided by x to the 1/2. Change my root into a fractional exponent. I got a quotient here, so I know I'm going to have to use my quotient rule, with u being 2x plus 8 and v being x to the 1/2. So my derivative is going to be, what is my derivative going to be here? Well, let's see. Derivative of u is going to be 2. Multiply that by v, which is x to the 1/2, minus my u, which is 2x plus 8. No, I haven't done the derivative of that. Now I'm going to do the derivative of, yeah. So it's u primed v, u, and then we'll have v primed over here, and the derivative of v primed is going to be 1/2 x to the negative 1/2. And then down in my denominator, I'm going to have x to the 1/2 all squared, which is v squared. Okay, so we want to set this equal to 0. So let's set it equal to 0, and let's start simplifying this whole thing here. So we need to, let's see, we'll have 2x to the 1/2, and we'll have minus 2 times 1/2 just gives us 1. Then x times x to the negative 1/2 is going to give us x to the 1/2. And then we're going to have the minus sign, and the 8 gives us minus 8 times 1/2 gives us 4 x to the negative 1/2. So there I've just expanded that, multiplied out all of my brackets. And of course at the bottom here, I've got x. I think. Okay. What can I do next? Yeah. So I can collect my like terms here on the top. 2x to the 1/2 minus x to the 1/2 is x to the 1/2 minus 4 x to the negative 1/2 all divided by x. And where should I go from here? What I'm going to do is I'm going to, I think the clearest thing to do is to look at my numerator here and factor out the lowest power of x. Okay. So my lowest power of x is, well, I've got x to the 1/2 and I've got x to the negative 1/2, so that's going to be x to the negative 1/2 that I'm going to factor out of my numerator. So if I take out x to the negative 1/2, I'm going to end up with x, okay, because x times x to the negative 1/2 gives me x to the 1/2 minus 4, all divided by x. Okay. And then my x to the negative 1/2, I can bring that down into the denominator. Where it's going to be x to the, not negative 1/2 anymore, but x to the 1/2 times x, which is just x to the 3 over 2. Okay. So that's as simple as this thing is going to get. And now we could just solve for our x value here. We've got 0 equals x minus 4 over x to the 3 over 2. We're interested in when the numerator is going to equal to 0. So our solution here is x equals 4. Okay. Yeah, we'll plug it back in. You might have, if you were looking back here at this line, sorry, right here, you might have said, okay, we're going to have two solutions, x equals 4 and x equals 0. But because we have an x down in the denominator, we can't have x equals 0. It's a restriction on our function. So we only have one solution, x equals 4. So we're going to sub this back into our original function. So we'll say y evaluated at x equals 4 is going to equal, what was our original function here? I've got to look back at this. 2x plus 8, so 2 times 4 plus 8, all divided by the square root of 4, which just gets us 16 over 2, which is 8. So the tangent is horizontal at the point 4, 8. And that's what they were asking for, so we are done.